Academy for this opportunity to present my work at this meeting. So I will be talking about plasma laboratories on megaparsec scales. This will be work mainly done at low radio frequencies using the Giant Meter Wave Radio Telescope, which is visible here on this slide at the bottom. So I'll introduce the topic of galaxy clusters and specifically which plasma I'm going to talk about and what is the significance of observations of these objects in radio bands and what we can learn from them. And I'll share some of the exciting new developments happening at the GMRT and in preparation to further developments across the globe. So to begin with, I would like to introduce what is this megaparsec scale that I am referring to. So our universe, as is familiar to us now, is that on the very large scales, it looks like a web, which is shown here. This is a simulation slice, which basically simulates the dark matter particles just under gravity. And in this web, these nodes or these bright points at the nodes are actually the most massive objects in the universe, so the most massive gravitationally bound objects in the universe, the galaxy clusters. And they have masses of the order of 10 to 15 solar masses. To give you an idea in kilograms, I have written these values here. And the size of a galaxy cluster is typically of the order of a megaparsec. And a megaparsec, to give you an idea of the scale, basically a parsec is about 300 light years. And if you want to compare it with the distance from Sun to Earth, it is a microparsec. A few times microparsec is what is the distance from Sun to Earth, and we are talking of scales of 10 raised to 6 parsec. So this is really something which definitely is unique in the universe, and the properties of these plasma that are on these scales are certainly different, and we need new methods to study them. About galaxy clusters themselves, they are composed of dark matter, mainly dark matter. Most of the matter mass in the cluster is actually dark matter, and a few percent is in the diffuse medium and in galaxies that we can see in our observing bands. So this is the baryonic component and this is the dark matter component. So essentially all the gravity basically in the cluster is due to dark matter, and in this deep potential well are these baryons, and due to this deep potential well, this diffuse gas is trapped there, and it is at a very high temperature. So to show you a picture of glimpse of galaxy clusters across the electromagnetic spectrum, the earliest views of galaxy clusters were in optical, the one shown here, and the same cluster, if you look at it in X-ray bands, it appears completely different. It is an extended X-ray source, and the mechanism of emission that is generating this X-ray emission is actually thermal Bremsstrahlung, and basically this plasma is at 10 raised to 7 to 10 raised to 8 Kelvin temperatures. And the processes that are operational in these systems are leptonic as well as hadronic. So some of the radiation mechanisms I have listed here: synchrotron Bremsstrahlung and inverse Compton scattering. And in the hadronic, we have the collisions between the relativistic protons and thermal protons and so on. And these are relevant for some of the things I'll be talking about later. And coming to radio bands, the lowest frequencies here on this electromagnetic spectrum. So in radio bands, I'm talking about less than 10 gigahertz observations. What generates radio emission is basically relativistic plasma and magnetic fields via the synchrotron mechanism, and these are generated in supernovae, the explosions of old stars within galaxies, the active galactic nuclei or the AGN, and they can produce these large-scale jets, which are basically relativistic plasma. And in galaxy clusters, we have spectacular systems with the X-ray gas, with these jets and lobes, and these interacting with each other. And these radio galaxies don't last forever, but they have a duty cycle, and then they switch off these particles that are emitted in the intercluster medium age, and they can have very different properties. I'm going to talk about cluster-wide diffuse radio sources, which are associated with the whole ICM as a whole. I'll be showing a lot of pictures with these contours. So in these pictures, the contours are the radio emission, and in color is the X-ray emission. So we see very large scale synchrotron sources in galaxy clusters. So the intercluster medium is composed of relativistic particles and magnetic fields. They are not detectable in most observable bands. But why low frequency bands are important are that the synchrotron emission with these GeV energy scale electrons and microgross level magnetic fields lead to detectable emission in radio bands. And as the spectrum loses energy, or the particles lose energy, the spectrum steepens, and as you go to lower and lower frequencies or long wavelengths, we are likely to detect the source for a longer time than at the higher frequencies. So that is where the critical observations with low frequencies come in order to even probe these sources, because they are mostly invisible at other bands. So there are many types of diffuse radio sources that have been detected in galaxy clusters. I have listed here 3 different types: the radio halos that are cluster-wide sources, radio relics that are at the peripheries of merging clusters, and these are arc-like polarized sources, and they trace shocks in cluster mergers. And there is also the third type, which is a mini halo, which is associated with the central bright galaxy in the galaxy cluster, and they are unique in their own ways. So the main thing is that these sources are extremely faint and difficult to detect. And the one question that is open is whether are these sources really rare, or is it just that we are unable to detect them. So to give you a glimpse of the plasma that we are dealing with when we deal with these relativistic electrons and magnetic fields and the thermal pool of electrons emitting the thermal bremsstrahlung. The issue here is that the magnetic field, although it is weak, plays a crucial role in particle distribution and transport. The mean free path of the particles is of the order of a kiloparsec as compared to the other length scales related to it, which are very, very small. So basically, there are nearly no collisions that happen, and literally the particles are tied to the magnetic field, and their transport happens via their motion along the magnetic fields. So basically, in this plasma, there are collective plasma processes which define the character of these phenomena, and those are the things that we try to probe using radio observations. So this plasma is what is called as a high beta plasma. So this beta is just the ratio of the thermal to magnetic pressure, and in this case, the thermal pressure dominates. So tied up with this plasma are a number of plasma processes. In particular, we have the shocks and the associated acceleration, and basically these leading to a generation of relativistic electrons, which we can detect as radio halos, relics, and so on. So all of this on the left is actually what we would like to probe using what we have in hand, which is basically mainly the radio and X-ray observations. So one of the main issues is how do these relativistic electrons come to be in the intracluster medium? Something has to provide them this energy. So definitely galaxies, active galactic nuclei, and radio galaxies are putting in these particles in the intercluster medium. However, the radiative lifetime is very short. It is of the order of 1 million years as compared to the lifetime of the cluster, which is several giga years. So they basically die out pretty quickly, and therefore you need something to re-energize them. There is another process through hadronic collisions that they can be produced. So both these sources on the left, the hadronic collisions and galaxies, jets, so on, produce these relativistic electrons, but they die out pretty quickly, and thus you need these reacceleration processes via shocks and turbulence However, these processors are very inefficient if they were to directly take the thermal pool electrons and reaccelerate them. Thus, these two mechanisms on the left, the idea is that they produce seed relativistic electrons, which are then accelerated to produce these cluster-wide sources. So we set out to look at the properties of these seeds because the simulations that predict the presence of halos, etc., they assume certain spectra for these seeds. However, through observations, this is not very well known. So, remnants of radio galaxies. So, remnants is a phase when the radio galaxy jets basically are no longer active. The central supermassive black hole is basically inactive and it doesn't produce new jets. So, whatever is already emitted just evolves in the medium, and that is what we call as a remnant. So, it will age passively in the plasma, surrounding plasma, unless it encounters something like a shock or a compression that can accelerate the remnant lobe, and we can see it again. Basically, it becomes detectable again. So we observed this kind of a source which was already known in this particular cluster, Eagle 4038, and we took advantage of the recently upgraded GMRT. So GMRT has undergone a major upgrade in the last 3 years or so, which has boosted its sensitivity by about a factor of 3. And it has, the improvement has considerably helped the detection of extended emission. So we set out to do these observations and got remarkably important results about these seed relativistic electrons. So on the left, you see the remnant radio galaxy in blue, which was known earlier, and with the new observations, we could map a much more aged and extended emission around this galaxy, which was missed earlier and also not modeled. So we got, thanks to the UGMRT broadband observations, we could get to map the spectrum in great detail, and we could in fact map the curvature in the spectrum across its extent, as shown here in the regions, in the circular regions here and the corresponding spectra. So we see that the seed relativistic electrons actually have a wide variety of spectral shapes, and a single power law-like behavior is not observed, but we see a variety in the spectra. So basically, we could measure the curvature, and this curvature basically implies that the spectra can evolve in many different ways as they interact with the surrounding plasma, thermal plasma, and these need to be accounted in simulations in order to make realistic predictions about how the relativistic electrons in the radio halos originate. So there is another work that I would like to briefly discuss here, which is about cluster mass. And so we know that merging clusters lead to this diffuse emission, and the question was whether massive merging clusters versus low mass clusters will make any difference. So we made two important discoveries. So we were looking at galaxy clusters at low masses, and we found two merging clusters which showed presence of shock and an associated relic. So this emission in red, shown in the right side panel, is the radio relic that we discovered, and we could make detailed spectral maps which led to the characterization of the shock in this cluster. So this was, at the time when it was discovered, this was the lowest mass cluster having such a relic. In fact, we broke our own record in a year when we discovered another one in a very low mass cluster. So this is basically a scaling between the radio power of the relics versus cluster mass, and these two relics are the ones which we discovered. And they basically, the scaling that we see in the power with mass is different from what one would expect from a simple model. For the sake of time, I will right now not get into this. However, simple scaling basically does not work, and we need to go into further details in modeling. So, because there are only a handful of such sources of radio halos relics known, There is still room for many new discoveries with more sensitive instruments coming up, such as the upgraded GMRT and so on. So this is a view of the survey that we had done a few years ago with the GMRT, and it took more than 200 hours of the GMRT observations to survey these various clusters shown on the celestial sphere. However, still new discoveries await, and the ongoing searches of galaxy clusters are throwing up new discoveries, and this is our last year's discovery of mini halo, which had properties of some properties of radio halos. So, given the new discoveries, one is starting to reclassify the already known broad classification between radio halos, mini halos, and so on. So, apart from the new observations, we have new challenges coming up with new, more sensitive facilities. So, the data volumes have gone up, and the analysis of such large volumes of data are a challenge. So in radio bands, what we measure is the Fourier transform of the sky, and we have to process the data in order to get the image of the sky. So this requires all the procedure, and now we have a pipeline that basically can do this analysis. And this is keeping in perspective the future developments. The other thing which we are doing to improve the sensitivity of the instrument is to actually mitigate this radio frequency interference. So basically terrestrial or satellite signals created by man which are interfering with our astronomical signals. So we have a new system implemented by the engineering team which we have commissioned and is recently being used. So there are many new results coming up with the upgraded GMRT, and we have the most sensitive images in these frequency bands. This is just a glimpse of the upcoming results. So in perspective, the large radio telescope called the Square Kilometer Array is being built by a large consortium of international consortium of which India is a full member. And this shows the current state of sensitivity of upgraded GMRT as compared to the SKA. And in this band, we are at the moment in the competitive range of sensitivities. And our aim is to do the science with this Pathfinder instrument. On the right, I have shown in blue all these points which are galaxy clusters, which will be probed by the surveys that can be done with the SKA, which will be located in South Africa and Australia. So we await a huge number of discoveries. So in summary, I would like to say that low frequency observations open windows to study the physics of this plasma on megaparsec-scales, which is otherwise completely elusive to detection. And the upgraded GMRT is providing an excellent opportunity towards developing our skills to prepare ourselves for the science with the SKA. And I showed you examples of the role of sea relativistic electrons and low mass emerging clusters where we are finding some surprising results. And we are also pursuing improvements in analysis methods and still learning along the way. So I will stop here